All right, lecture 48. We're going to do a couple of examples with a hypothesis testing with paired data. All right, first example, grip strength differences, 36 women. So already the sample size is bigger than or equal to 30, right? Between the ages of 20 and 24 were tested for grip strength in both the right and left arms using a dynameter which provides grip strength measurements in pounds. Part of the sample data is shown below. So subject A had a grip strength of 72 pounds in her right arm and a grip strength of 64 pounds in her left. Right minus left gives us 8 pounds. Subject B, 69 minus 72 gives us 7, etc., etc. So, of course, the sample of data that we need for the problem here that we're interested in is that sample of differences. So the sample of differences begins, what did I say? 72 minus 64 is 8. 69 minus 62 is 7. Then if you look at the next one, the difference is 4. Look at the next one, the difference is 6, etc. All right, there are 36 data points. 36 data points because there are 36 differences, one for each woman, doing right minus left. We compute D bar, the sample mean of this 36, to be 8.1 pounds. And S sub D, which again means the sample standard deviation for the set D of differences, set of differences D, where you think of these, here's a D value, here's a D value, here's a D value, so I'm kind of thinking my random variable is D, so S sub D for this sample turns out to be, what do I say, 3.6 pounds. All right. Let's test the claim that in terms of grip strength, 20 to 24-year-old women are, on average, stronger in their right arms. We'll test at the 1% significance level. So alpha equals 1%. All right, first off, what are the null and alternative hypotheses? What do I say here? I say that take that quote, or that little phrase I lifted out, on average stronger in their right arms. We have to interpret that in such a way that we can get a null hypothesis and an alternative hypothesis out of it, all right? On average, of course, we're going to get a mean, in other words, and what it really means, I have here that if mu is the population mean of right minus left arm strength, trying to use different markers so that it's not as squeaky. Got some newer markers here, but it still does squeak some. For this group of women, for let's say 20 to 24-year-old women, year-old women, 20 to 24-year-old women, then we're making the claim, or rather the two hypotheses are, if we want to make the claim that on average they're stronger in their right arm, then the null hypothesis is going to be that this mean difference, right minus left, is 0 pounds. And H1, if we think they're stronger, or the claim we're making then is that mu is greater than 0. So it's a right-tailed test, right? Right-tailed. Okay, I guess I got to do it here. The t-curve. So I have degrees of freedom are 36 minus 1 is 35, right? So I have like that. And what? I'm testing it at the alpha equal 1% significance level. So out here, I have area equals 0.01. And what is my critical value? It turns out to be, if you look in the table, it turns out to be 2.438. So this is T sub 0.01 for the T curve that has degrees of freedom 35. And it is, what did I just say, 2.438. All right, test statistic. Test statistic is the t-score of the sample mean, d bar. So it's d bar under the assumption that H naught is true. So under the assumption that, here's my mu naught, right? So it's d bar minus mu naught over S sub d over the square root of n. So we get d bar is given to be 8.1. And we're assuming under the assumption of H naught that the mu is actually 0. So it's 8.1 minus 0 over S is 3.6 divided by the square root of 36. Made the numbers come out nicely. And it works out to be 13.5. Okay, so where is that? That's way the heck out here, right? Definitely in the rejection region. I didn't write rejection region there. You know by now that that's what that is. For we reject H naught. Our conclusion then, at the 1% significance level, I'm going to abbreviate a little bit here. At the 1% significance level, there is sufficient evidence to reject the claim that the mean of the differences in strength is 0. To reject the claim that the mean, let's say right minus left grip strength is 0. It appears to be greater than 0. It appears that on average, 20 to 24-year-old women are stronger in their right arms. It appears that on average, and that phrase on average is used a lot. It doesn't necessarily have a precise statistical meaning, but what we mean when we say on average, we are talking about the mean, right? So I'm going to say here, it appears that on average, 20 to 24-year-old women are stronger, well, their grip strength is greater, stronger in grip strength in their right arms. Not surprising. And I also put here, just to get our discussion of statistical significance into play, we could say result significant at the 1% level. Right? We rejected the null at the 1% level. Make sense? Terrific. All right, let's do another example. Tumor shrinkage. So why don't you read that paragraph while I rub some of this out. So back in, what did I say, lecture 45, we did a hypothesis test involving tumor shrinkage, and I can't remember now if I mentioned that the way we did it wasn't usually the standard way that it would be done in the scientific literature. But we didn't have the tools developed to do it quite the way that we should do it, but now we do. So now, if you read that paragraph, you'll see that we're going to do it in a more realistic way. Okay. So, as I say, the realistic way to do it, of course, is to measure the effectiveness of the treatment if you can measure the individual tumors before and after the treatment, and then look at the differences and see if it really did look like it shrunk these particular tumors, right? What I say here, we test 25 subjects by measuring tumor diameter before treatment and again 8 weeks after beginning treatment. And 25 is less than 30, right? 25 less than 30. So what are we doing? Well, we're going to assume that these differences are normal. Assume differences come from a normal population. funny U. Assume they come from a normal population. Therefore, we don't need n to be bigger than or equal to 30. We know that we compute a z-score. It really is normally distributed, normal 0, 1. We compute a t-score. We can trust that it is t-distributed, or close enough. All right, so yeah, what do I say then? I say that, so we do the before and after. Difference of diameters, right? We're doing diameters, right? And the difference is, the sample mean is minus 2.2 millimeters. So d bar is minus 2.2 millimeters, and somewhere there I think I say we're measuring tumor diameter. And the sample standard deviation, of the sample is 1.4 millimeters. Okay? So we're going to test at the 2.5% significance level, 2.5%. All right, well, we're just going to run through the same outline. So as before, what do I say here? I say we have to, again, interpret correctly so that when we interpret what we're talking about directly, so we write down the null and alternative hypothesis, they'll make sense, right? So let's decide what mu is, because that's what the null and alternative hypothesis is about. So what I say here is, if mu is, what we want it to be, of course, is the population mean of the differences. If mu is, and this is an important step to write this in so it is clear what the mean is, right? The data that we are given, if we were actually doing the work, is just diameters, correct? Before and after. And we're pairing them up and subtracting for each tumor, the before diameter minus or I guess we're doing after minus before here. We're doing after minus before. That's what I say, isn't it? 8 weeks after and find the difference. Yeah, after minus before. And those are the things, those measurements are the ones we're interested in. Those are the ones we want the population mean of. So if the mu is the population mean of the differences for the tumor diameters after minus before, if mu is the population mean of tumor diameters after minus before, then H naught, nothing happened. H1, I want it to be, if I'm doing after minus before, I'm hoping for shrinkage. So most of the time I want this to be smaller than that, so the difference should be negative. All right, so you have to think through what the mean is in terms of the situation, and it depends on which way you're doing the subtraction, right, to determine what test you want here. And this is left-tailed, right? And of course, we could have done it the other way around, just like in this problem over here that we just did. We could have switched it the other way around. It would change whether we're doing a left-tailed or a right-tailed test. But the way we have it set up, this is good and solid, and we can go forward. All right. Picture again. Picture of the curve. All right. This is T, and the degrees of freedom are 24, right? 25 minus 1. Shouldn't touch right here, but oh well. It's a left-tailed test. So the area out here is going to be 0.025. That's the area, right? Because it's a 2.5% test. And the critical value, so the critical value is negative T.025. And I look that up and I get, doggone it, I don't have it. That's funny. I don't have the number, and I don't have my table here. Anyway, so I don't know what it is, but it's not going to matter. It's something. You can look it up. I don't know why I don't have it, but that's okay. It's okay because the test statistic is going to end up being way the heck out there. So I'm not going to have to wonder if it's in the rejection region or not. Right? If you've paused me, as of course you always should be doing, you should have all this worked out already. And you would know that. So I hope you're doing that. As I said before, I forget to tell you, okay, pause me and do this. But that's always implicit. When you look at this and say, okay, this is like what I've done before, then pause me, do it all, and then start me up and see if we all did it the same way. All right, so the test statistic is the t-score, d bar minus mu 0 over s sub d over the square root of n. And so d bar is negative 2.2. This measured millimeters. The mean change under the null hypothesis is 0. It's minus 0 over the standard deviation. Sample standard deviation is 1.4 divided by the square root of 25, right? And if you work that all out, you get negative 8. Can I fit it in there? Yeah. Negative 8. All right, so where does that lie? Like I said, I don't know what this critical value is, but negative 8 lies way the heck out. I know it isn't negative 8. I know it's way in from that. So I don't know what the number is, but it doesn't matter. So we're way out there again. So again, we want to reject. What do we want to reject? We want to reject H naught pretty handily. All right, so what do we want to say? You should be writing it out. At the 2.5% significance level, there is sufficient evidence to reject the claim that the mean, that the, let's say, after minus before mean difference in tumor size is 0. Sufficient evidence to reject that. It appears that there really is a drop in tumor size. So what do I say here? I say it appears to be negative, i.e., it appears the treatment does shrink tumors. It appears the treatment does shrink tumors. You could say that tumor shrinkage is statistically significant at the 2.5% significance level. It's actually statistically significant at even much lower levels because negative 8, way the heck out here, you could slide that critical value out quite a bit and have a much smaller alpha, and you'd still, the test statistic would be in the rejection region. Let's stop.